All right, guys, am I on? Can somebody give me a thumbs up or something? Can you guys hear me today? Yes, okay. I'll take that as a yes, Benjamin, thank you. No. All right. Seriously, we have only 8 people today?
That's kind of sad, right?
Yeah, I mean, I sympathize. I am kind of exhausted by the whole Zoom experience. I have to do Zoom meetings as well. I'm not only just the teacher for you guys, but I sit and after an hour of listening to somebody else drone on, I need to go get a drink or something. So I know this is hard. For the most part, you guys have been troopers, but that's a big drop. And it's a pity, actually, because as we get to the end of the semester here, we're actually getting to the very best theorems, the part that makes this feel the coolest out of the whole semester. Well, let's get started anyway. Do you guys have comments or questions on the homework? It's not due tonight. It won't. I guess I said it due on Friday night. Actually, I don't remember when I said it due.
Yeah, it's Friday.
Friday night, yeah. Okay, yeah, I'm not supposed to, ordinarily at least, I'm not supposed to set anything to come due on the, what do you call them, the no class days, which I guess are next Monday and Tuesday. So I have to have it wrapped up, have things wrapped up before then, and I didn't want to have you guys lose your last weekend before finals, so I made it on Friday. Anyway, questions or comments on the homework set or the material that we've been looking at? All right. I do want to continue with Stokes' theorem and also take you into the last theorem, which is Gauss's divergence theorem. That's on the docket for today. But before I do that, I want to clarify our schedules. People have been asking me about the final exam, and I guess I've sort of fallen into a decision without really checking with you guys. Let me show you the calendar that I've been setting up. So this is the last 2 weeks of the semester. We're halfway through the top line. The classes end on the 8th, which is this coming Friday. So I'll put a cross through that. That's done. That's done. So we have class today and we have class on Friday. I'm not sure if we'll be able to get through the slides. I wrote up my slides in advance today to try to present the material I wanted you guys to see. If we have to continue on Friday, I'm happy. Also, I want to leave time on Friday for a review so that you guys are ready.
Dr. Russell, you cut out for a little bit. Do you mind? I said you cut out for a little bit.
Missing it. I don't know what's going on with this mic and camera. And I know it's hard for you guys to see. All right. But am I back now? You guys can hear me?
Yes.
Thank you. All right, so so this is what I was thinking of for the calendar. We just finished this week, regular classes. Next week is when the exams start. Now, I'm going to have one common exam for both of the sections of 427L that I'm teaching. One has an exam scheduled for 9 a.m. on Wednesday the 13th, so that's 1 week from today. And the other has its exam scheduled for 7 to 10 p.m. on Saturday the 16th. So my thinking is that I will make the exam available to you guys as of Wednesday morning at 9, and it'll be due by Saturday afternoon, or Saturday evening at 10 p.m. And that way you can do the exam at your regular scheduled hours if you like, or pick another time in there that you want to work on it. So as with the last exam, there will be both a free response portion, which you can work on all the way from 9 a.m. to 10 p.m., and a quest portion, which I will let you start it whenever you want, but you'll just have, I don't know, maybe 4 hours to work on the whole thing. So that would be the exam. I would like to have open office hours on this coming Monday, maybe starting at 11 o'clock like this class, and I'll go for a couple of hours, 1 p.m. And I am available to have extra hours added if you guys need me, but keep in mind I do want you to start the exam on Wednesday, so don't wait until Tuesday night to decide that you need some help. And on behalf of parents everywhere, let me advertise that this coming Sunday is Mother's Day. If you have a mother or a mother figure that you need to honor, then don't be doing your math homework on that day, unless that would be something that makes her happy. So, anything that I need to clarify about the schedule here? Okay. Then let's get back to the material. And this is where we last were talking. I had presented Stokes' theorem to you, and it is a mouthful. It's got a lot of stuff in it. But it falls in the same category as the fundamental theorem of calculus and Green's theorem. Both of those theorems can be set up as stating that an integral of one kind of dimension is equal to an integral of the next higher dimension. And exactly what that means depends on context. But, well, I'll show you maybe Friday how they actually are all special cases of one thing. But the Stokes theorem version says that a certain line integral will match a certain surface integral. And the line integral over here is just, well, a completely general line integral. It's the kind with the dot product in it. So it's assumed that you do have a vector field. The capital F stands for a vector field, and you're going to integrate this around a curve. This is the one where you have to take the dot product with the tangent vector, the velocity vector. And the curve in question is going to be the boundary of your surface S. That's the surface that shows up on this side. So the boundary of a disk, for example, is the circle that's around the edge. But even if that disk is not flat, if you let it get kind of puffy into a a hemisphere, the boundary would just be the places along the edge of the hemisphere where you can sort of fall off. So that's the surface S shows up on this side, and its boundary is on that side. The rest of the right-hand side is a surface integral to be computed over that surface, but it's not directly the kind of surface integral where you chop up and multiply values of a function times an area. This is one of those ones that has a vector field involved. And so you would start off with this vector field. It's actually the curl of the vector field that was on that side. You have to take the dot product with the unit normal vector. And then you can do the chopping up and multiplying areas times values of the function. Okay, so it's that those two types of integrals are the ones involved in Stokes' theorem. Let me clarify something that I did get as a question in an office hour, that this is a very general theorem in the sense that the surface that's being referred to over here can be basically any surface. I mean, there are some technical conditions that we'll have to discuss, but you don't, in practice, you won't need to worry about those. And the vector field over here can be any vector field in R3. And again, there's some constraints about smoothness and so on, but for our course, I don't want to stress those things. So that's what I said here. You can start off with an arbitrary vector field on this side. And of course, this being a surface integral with the dot product involved, you need a vector field on this side too, but the one on this side is supposed to be the curl of that one. And you may remember from the definition of curl, it involves some partial derivatives. So this is some kind of a curl of the vector field you have on the left. Arbitrary vector field here, and then you differentiate it to get the thing on this side. And in the same way, the surface is basically arbitrary on this side, but then the curve that you have on this side is not an arbitrary curve. It has to be the boundary of the surface S. So in any integration problem, there's always three things that you can play with. Somebody can give you any set to integrate over, any function to integrate, and any kind of means of measuring size, which naturally would be some sort of a length on the curve or area on the surface. But for sure, the thing you're integrating over and the thing that the integrand are kind of, they could be anything. There doesn't have to be any relationship between those two things. But in Stokes' theorem, the two integrands are related by the one on the left is arbitrary, the one on the right is its derivative. And of the two places you're integrating, the surface on the right is arbitrary, on the one on the left is its boundary. So I'm saying that in a lot of detail here for Stokes' theorem. I actually kind of said it as well for Green's theorem. I don't know if you guys were hearing me, but I'll say it again for Gauss's theorem when we get there later today or on Friday. And I'll also go back and say it's true when you go all the way back to the fundamental theorem of calculus. This is a one-dimensional integral. There's lengths involved, and a two-dimensional integral, which is surfaces. The fundamental theorem of calculus was one dimension down. So this was a one-dimensional integral, just an ordinary integral across an interval in the real number line. And that's a zero-dimensional integral, where you're literally just multiplying values of the function times the size of the portion of this set. So you could put any function on that side, but its derivative needs to show up on this side. And you could have any interval on that side, but its boundary shows up on that side. The boundary of an interval is only 2 points. So there's really two values of the function that have to be added. And for the fundamental theorem of calculus, we just did this in the real number line. This was any function of one variable. This just meant its ordinary derivative. But it was kind of what I'm saying here about Stokes' theorem is analogous to what you can find in the fundamental theorem of calculus. One more technicality we have to worry about, and that is in the fundamental theorem of calculus, the intervals have a clear direction. They move from left to right. Or the way you would write things in Calc 1, you would have a lower limit of integration and an upper limit of integration. And even if you had a bigger number there and a smaller number there, you had to keep track of which was the bottom number and the top number, because when you look at the boundary of that interval, it only had 2 points, but you considered one of them as being accompanied by a plus sign and the other one as having a minus sign. So there's a kind of an orientation on this set of just 2 points. And the same thing is true here. In order to compute a surface integral on the right-hand side, you have to pick a normal vector at each point of the surface. I don't care which one you pick, but you got to pick it in order for this right-hand side to make sense. Likewise, on the left-hand side, in order to compute the line integral, you have to know which of the two possible tangent vectors you're going to use. And in order for Stokes' theorem to be true, you have to make that choice consistent with whatever choice you had on the right-hand side. So Pick an ordering of your two endpoints, and then we'll decide which one is going to have a positive and a negative. And pick an orientation for your surface, the collection of normal vectors to the surface, and I will use that to pick out which of the two directions you should walk along the curve. And we talked about that last time. I said that you should be keeping your head up, where up means in the direction of the normal vector, and then keep your left hand dragging along the inside of the surface, and from that position you try to walk forward. So that was what we call the induced orientation on the curve. All right. Do you have any questions about this generality of what Stokes' theorem says? Now, you guys are going to have an open book exam for the final because I don't know any other way to police it. So I guess you're off the hook. You don't technically have to memorize this theorem, but I would like you to kind of remember how it goes, even on your own without looking in a book. All right. Oop, I have to click somebody in here. There we go. All right, so if you guys don't have any questions about the general statement of Stokes' theorem, let me show you some of the special cases of it that are kind of memorable or most useful. And they'll be mostly like the special cases we had for Green's theorem. I got you into the whole curl business in the first place when I wrote out Green's theorem and then recognized that the right-hand side of Green's theorem did look like a curl. So that's the first observation, is if your surface happens to lie just in the xy plane of three-dimensional space, that's the surface, right? A disk that just lies down there on the xy plane. You can still think of that as a surface floating in three-dimensional space. Doesn't float much, but anyway, it's in there. And if your vector field is also just described as a function of just the x and y coordinates, and the z coordinate is always a 0, then that's obviously a very special situation. I've just made a lot of restrictions. And yet, if you make all of those restrictions, what you have written down as Stokes' theorem becomes exactly Green's theorem. So you don't, on some level, you never have to remember Green's theorem again. It's just a special case of Stokes' theorem. The next special case that I guess we've talked about a little, or at least we certainly did for Green's theorem, is what happens when the vector field happens to be the gradient of a scalar valued function. Now it'll be a function of 3 variables, since all of this Stokes' theorem stuff is in R3. But if you take the gradient of a function of 3 variables, you'll get a vector field in R3, and that vector field is special compared to most vector fields, because such a vector field has a curl, which is the 0 vector field. This is one of our special rules about curls and gradients, is the curl of the gradient of a function always comes out to be 0. It's one of those times when when this funny notation for curl is a nice mnemonic, because you remember that when you take the cross product of any vector with itself, you always get the 0 vector. And well, this gradient symbol isn't really a vector, but I write it out as a vector. Anyway, it's a fact about vector fields that the curl of the gradient of a function is the 0 vector field. And as a consequence, if you start off with that kind of a vector field on the left-hand side, then the vector field that shows up on the right-hand side is now the 0 vector field. And if you take the dot product of that with your unit normals, you'll just get the number 0 at each point on the surface. And so your integral will be 0. So in fact, you don't really need this curl to be the 0 vector field everywhere, but even if you just know for whatever reason that the curl of your vector field f happens to come out to be the 0 vector field at each point along the surface, that's enough. It could be non-zero off the surface and you don't care, because in this example you're only integrating over the surface in the first place. Anyway, the way I wrote it out here is to show you what happens then. The other side of Stokes' theorem says that a certain line integral will be 0, and as I said, you do have to have a kind of a special vector field, but apart from this restriction, you could put any vector field f there and integrate along the curve C and you'll get 0. But I do have to stress that this curve is supposed to be the boundary of the surface that was on the right-hand side of Stokes' theorem. And I know the right-hand side of Stokes' theorem just disappeared. It turned into a 0. But we're still using Stokes' theorem, which says you have to have a surface in mind over here. And that surface has to give you, the boundary of that surface has to give you the curve that you're using on this side. So what that will mean in practice is that you can only do this when the curve C is a closed curve. It has to begin and end at the same point. That's a kind of a topological fact, a geometric fact. If you take any surface, like before I had you guys envisioning a hemisphere, then the boundary of it will have no boundary of its own. Just to give you another example, look at the left-hand side of this. This is my glasses case. And if you just look at this surface here, its boundary would be this curve that goes along the rim. It takes a little hop out there and then continues all the way around, and it comes back to where it started. So that will for sure be a closed curve. There's no endpoints to that curve. And so that will restrict the kinds of curves for which you can expect to get some mileage out of Stokes' theorem, even if you have a pretty vector field like this. I'll say one more thing too, just as a little sidebar. In general, if I give you a closed curve, you can probably find a surface that has that curve as its boundary. In fact, you can probably find a lot of curves that have that surface as its boundary. Just to give you an illustration, if I draw a closed curve here, this rubber band is now a closed curve, that can be thought of as the boundary of the little disc that lies on the paper. It's also the boundary of a little hemisphere that pops out of it. And you can you could use the lower hemisphere. That would have the same boundary. Another example is if you bend this rubber band a little bit, I'm making, I don't know how to describe this. This curve now is like the boundary of a Pringle, but you could actually suspend a Pringle on this thing in two different ways and have it come out to be the boundary. You could have it be sort of filling in the space between the two low parts, so stretching across the top of the Pringle, or it could fill in the space between my fingers, between the low parts, between the high parts of the curve, so it would stretch across the bottom. I'm sorry that your flat computer screens are not allowing you to see the 3D shape very well. But it is a thing that for all of our examples in this class, whenever I give you a closed curve, you will usually be able to find a surface, and many surfaces, in fact, that have that boundary. It won't matter which one you use in Stokes' theorem in this case, because no matter which of those surfaces you use, this line integral will turn out to be 0. But for comparison, I will draw your attention to what's called the trefoil knot. So there is a branch of math called knot theory, and what you look at is how different closed curves can be embedded into three-dimensional space. So this is, you're supposed to see the curve kind of passing behind itself and on top of itself where there's little breaks. But just imagine that there are really no breaks, you have to kind of stitch things together. That would be an example of a closed curve, but it isn't really the boundary of any surface. There's no surface that would have exactly that thing as its boundary. So I won't try to twist your brain a little bit. I won't be giving you any closed curves that look like this. All of the closed curves that I give you will be the boundaries of a surface. Now, this looks really cool because, it says that a lot of line integrals will be 0, but it did have to be a closed curve here, and it did have to be a special kind of vector field. The next special case that I want to draw to your attention is a little less special in the sense that if you don't have a closed curve, you can still say something if you do still have a vector field that's at least that is a gradient of something else. And this is something that we saw in the context of Green's theorem. If you know that your vector field is curl-free, the curl of it comes out to be 0. So that's a conservative vector field. It's the gradient of some function. Keep that premise. then even if you don't have a closed curve, you can still say something about this line integral. Namely, you can say that the evaluation of the line integral is independent of the path that you use to get from A to B. And the rationale for this so in here is exactly the same as it was for Green's theorem. If you subtract this line integral minus that line integral, you'll be taking the line integral of the vector field f first along that curve and then along this curve run backwards. But if you first go from A to B along C1 and then you go from B to A backwards along C2, then you just made a closed curve. And so the rest of this over there says that that difference between the left and right sides is 0. So we do use this. In fact, I know how to compute what this is equal to. It's just going to be actually f of b minus f of a, where f is any function whose gradient really was capital F. For you physics-minded people, this is asking you to compute the amount of work done to move from point A to point B. And it doesn't matter which path you use, in part because you can compute that work done by simply subtracting the values of the potential energy function at the end and at the beginning. Now, the next special case of Stokes' theorem that I want you guys to be ready to use covers what if you don't have such a special vector field? What if it isn't the gradient of something else? And then, well, then I would say use Green's theorem, excuse me, Stokes' theorem. But I can make a result that's analogous to this one. And here's how it would run. You give me any vector field that you wish to compute on a line integral and any path that connects a couple of points. So here's your just completely generic line integral to be computed, the kind with a dot product in it. What you get out of Stokes' theorem is that if you want, you can change that curve to any other curve that has the same beginning and ending points. But you won't necessarily get exactly the same value. You have to put in a correction term. And this is something that we did for Green's theorem as well. So that all I'm going to put in here for this, this correction term is exactly what the right-hand side of Stokes' theorem says you need to do. You need to compute a surface integral of the curl of that vector field f, and you integrate it over this surface, which is the space between those two curves. As I said before, you can have actually a lot of surfaces that'll fill in that space. So there's some latitude here. You can choose not only the curve, the other curve that's going to join A to B, but you can choose which surface you use to fill in that space. As long as you choose a surface that has the curves C1 and C2 as its boundary, then you can go ahead and compute this surface integral and you'll get the correction term that says how much this line integral will differ from that line integral. The only little caveat you have to be aware of is that when you compute a surface integral, you do have to pick out the normal vector and you have to choose it in such a way that it matches the orientations that you have on C1 and C2. Okay, so we talked about the orientations earlier. But this, in practice, you know, Stokes' theorem can be used, like all of our theorems. When they say any of the theorems that says the two integrals are equal, you might use that in practice when you start on the left and you want to rewrite it as something on the right, or you start on the right sometimes and you want to rewrite it as something on the left. But this special case is usually used when somebody gives you a line integral that you don't like. You write it as a line integral that you like better, plus a surface integral which you hope is not going to be too complicated. You guys are being quiet, so I'm going to assume you're still following me. All right, so all of those special cases were just like things that I said for Green's theorem. I've got another kind of a special case of Stokes' theorem, though, that didn't have an analog back when we were discussing Green's theorem. And that is that sometimes you can have surfaces that don't have any boundary at all. And a natural case for that would be something like the sphere. The upper hemisphere has the equator as the boundary, but the lower hemisphere has the same equator as the boundary. And actually, if you use a consistent normal vector, like the outward-facing normal on the sphere, then when you look at the orientations that each of the hemispheres would force you to use on the equator, you would see that they're backwards from each other. And so integrating along the equator, the two contributions would cancel out. So there's really no boundary on the sphere. It's an empty boundary. And the sphere is not the only kind of shape that does that. I mean, you could put a dimple in the top of the sphere or something like that. You could imagine it's made out of silly putty and start to stretch it into different shapes. But none of those would have a boundary. And other shapes don't have a boundary either. So this is a torus, a donut, an inner tube. And it has no boundary. There's no place that you could be standing on this surface and worry that if you started walking in the wrong direction, you'd fall off. By the way, I want you to notice my artistry in here. When you wanted to draw if you wanted to draw a donut, a lot of people would put a circle inside a circle, but what your eye sees in this case is a washer like you had in Calc 1 or Calc 2, and that's not what I mean. So what you do is you put two little pieces of parabolas or something in there, and then it becomes a three-dimensional shape. So that one's called a torus. Anyway, in all of these cases, you have no boundary. So on the left-hand side, you get nothing. You're just going to get a 0. Of course, you have to be integrating a curl of some other vector field in order to apply Stokes' theorem in the first place. But that's the conclusion that you get, is if you integrate a vector field over a surface that has no boundary, you will for sure get a 0 if the vector field you're calculating happens to be the curl of something else. Now, we have talked about this a little bit. How do you recognize when a vector field is a curl of something else? And the answer is it's not always true. You know, back in the Calc 1 days, if I gave you a function to integrate, you might say, well, is the function that I have been given, is it the derivative of something? And the answer was yes. You spent all of Calc 2 looking for antiderivatives. But now in our setting, you might want to try to go from right to left, and you're asking yourself, well, I've got a vector field on the right-hand side. Is it the curl of something? And the answer is not always yes. So there will be times when you can't use Stokes' theorem to go from a right-hand side to a left-hand side. And that's certainly the case here. If you saw you had a surface with no boundary, you might get excited thinking your integral is going to be a 0, but that's only true if the vector field you're trying to integrate is a curl of something. So, okay, it's a cool looking application. It might be limited because you just don't know about your vector field sometimes.
How can you check if your vector field is the curl of something? Do you check if the divergence is 0?
Ah, yes, exactly true. So we were going to get to that when I get to Gauss's divergence theorem. So that one is about divergence. But yes, you are correct. Again, there's some sort of technical hypotheses that you have to check, some interesting special cases. But I'll just say that as a little sidebar here. If somebody gave you a vector field G and asked, is it the curl of something? I'll put a little question mark over this F. Oh, no, maybe I should put it over here. Is your vector field G, is it the curl of something? Then the answer is that's yes, but if and only if the divergence of your vector field G is the scalar field that's always equal to 0. So again, this is a theorem, and every theorem has hypotheses, and I'm not mentioning them for you right now, but they won't get in our way in this course. So yeah, that'll be the check that you use.
Partial S represent there.
The partial symbol in front of a geometric set always means its boundary. So here I'm drawing surfaces, and that means the boundary of the surface. So thanks for asking. And specifically, I would be using this on curves and surfaces that already have an orientation, little arrows drawn on them. And then when you look at the boundary, that's another geometric set, but it gets arrows put on it as well. So that's a lot of words, but just in one word, that stands for boundary. Boundary of. 2 words.
Cool, thank you.
Yeah, you guys got to keep asking me this because I know the notation at this point is starting to get really complicated. That's just the notation. There's also the underlying principles, to say nothing of the proofs and the applications. So this is hard stuff here. All right. So I have another little sidebar for you. All of the stuff that I've been saying about, everything I just was saying about surfaces, for example, and this thing as well. When you want to use all of these theorems, like Stokes' theorem and the next theorem as well, you do have to assume that you have the ability to put a consistent bunch of arrows on your surface. I mean, you can see me doing it here. I just chose to start putting outward-facing arrows at each point on the sphere. If I start wandering around the sphere, my direction of my arrows is going to change, but only a little bit as you move from one point to another one. You can continuously vary the direction of that sphere, of that arrow, as you wander around the sphere, and you know, there's a smooth way to do that. Same thing on the torus. I could consistently have the arrows be pointing outwards, for example. When you can do that, then you say that your surface is orientable. We're putting an orientation on the sphere, so, and I can do that, or whatever the surface is, I can do that because my surfaces have an orientation. It doesn't have to feel always natural, as long as it varies in a continuous way. But there are surfaces for which you cannot do that. And the simplest example is the Möbius strip. And perhaps you guys have made these things in even in your grade school classrooms. I don't know if you can see from my picture what I want you to do, but I imagined taking a strip of paper, and I drew little arrows on it to show up and down, but then I glued the pieces in a way where those arrows didn't match. And you would see if you tried to make a unit normal at each point on this surface, then those normal vectors would, well, they have to be normal. They have to point perpendicular to the surface. And you would run into trouble trying to do that in a consistent way across the whole surface. I can't really show you in that illustration, but I've made a visual aid, and I invite you to make one yourself. So I took a strip of paper with a white side and a blue side, a clear side and a shaded side, and I've clearly indicated which edge of this strip I consider to be the top edge. So there's arrows pointing to the top edge on that side, and if you flip it over, I've drawn the arrows still pointing to the same top edge of the paper. When you make the Möbius strip, you bring the edges together, the short edges together, but before you glue it, you make a twist. And when you perform that operation, you now have a surface. It's a perfectly fine surface, and I could ask you to compute integrals of scalar valued functions on there, and they would mean what integrals always mean. You would chop this strip into a bunch of little squares or something, and you multiply the area of each one of those pieces times the value of your scalar valued function on there. So there's no difficulty in computing the first kind of surface integral that we looked at on such a surface. It would be more difficult, however, if I asked you to do something with vector fields, because you know the way we have to compute our integrals with a vector field starts by choosing a unit vector that's normal to the surface at each point. And I guess you could pick either one. I guess I would, the way I'm holding my pen here has the normal vector kind of going up away from the blue surface. And so you would begin with your arrows pointing outwards. I don't know, right at this moment it's pointing towards the camera. That would come up out of the blue side. By the time you twist around though, kind of come out of the blue side would have you facing that direction, and then this direction, and then this direction. And then by the time you get over here, it's pointing in that direction. And finally, by the time you come back up to the top where these two pieces of paper are glued, now the little arrow would be pointing downwards. And so I would have an abrupt change from this side of the short edge of the Möbius strip where I glued it to the white side. So this is what's called a non-orientable surface. You cannot, in a consistent way, continuous way, figure out which of a choice of the two unit normal vectors at each point on the surface. So you will never be able to even make sense of the kind of surface integrals that involve that normal vector, the ones that involve dot products. I can't ever ask you to compute such a vector, an integral on such a surface. you would have to look at me in the face and say, I have no idea what you're talking about, and I bet you don't either. And I would have to confess I don't. So I won't ask you to do that in this class, but you could ask for some kinds of integrals over this thing, and you could anyway worry about what happens if you try to compute something with the unit normals, because there isn't a consistent way to pick the unit normal vector with a continuous choice all the way across that surface. For you math majors out there, let me just tell you, these are the beginnings of topology. There's all kinds of interesting questions that we ask in the topology course about curves and surfaces and so on. Lots of really cool theorems. Another one that I will give to you is that on the surface of the sphere, it is possible in a continuous way to pick out a normal vector to the sphere. But what if I ask you to find a continuous choice of a tangent vector to the sphere? So how could I have the wind blowing across the entire surface of the sphere at once? It's very easy to just ask for the wind to blow eastward everywhere, but east doesn't make any sense at the North Pole and the South Pole. So which you could interpret what I've just been describing here by saying, I can have the wind blow everywhere on the surface of the Earth in a nice smooth way, except at the 2 points the wind couldn't be blowing. Or in another way to say it is, you could take the hair on a sphere and comb it down in a nice, well-defined direction everywhere, but you'd end up with a little cowlick here at the North and South poles where the hair wouldn't have anywhere to go. And that's a theorem, is that there's no way to comb the hair on a sphere.
So if the vector field wasn't a curl, what would you get instead of 0?
Here?
Yeah.
Well, you're asking me, is there any interesting way to compute a general surface integral of any vector field? I guess you're not putting any restrictions on the vector field. You just want to put a G here. How the heck am I supposed to compute a vector field, dotted TS, over a general surface? And, well, Stokes' theorem isn't going to give you any help there. What will be useful in this case, if your boundary is empty, we will be able to say something about that, even for non-curled vector fields. I will give you an answer, but that comes from the other theorem that we have yet to talk about, which is Gauss's theorem. So stay tuned. It's a good question, but I didn't give you an answer yet.
So could you, though, if you had that sphere, right?
Yeah.
Could you cut it at the equator, and then you would have 2 separate hemispheres, which each have a boundary that's non-zero?
Yes, but then how does that help you? You still can't use.
You just add them together. And you
yes. Well, you can always compute the vector. You can compute this integral. I mean, I had you guys computing integrals, even over a sphere, over a surface with no boundary. There's no difficulty in doing this. You parameterize the surface. You evaluate your vector field at each point with the parameterization. This is where the TU cross TV comes in. You dot that cross product with the vector field you've got. And now you'll have an integral defined over all thetas and phis that you use to parameterize the sphere. So there's no difficulty in computing it. Yeah. You were just hoping for an easy answer, and there isn't going to be one. At least not from Stokes' theorem.
Fair enough.
All right. Now look, I do want to talk about that Gauss's theorem. It may not come until Friday, but the other thing I want to make sure you guys have seen an example of is I wanted to grind out Stokes' theorem in one example. And as I said at the very beginning, you could have any vector field and any surface, so I chose a kind of random looking pair. Here is a vector field in R3, no pattern, it's just 3 functions of x, y, and z. Here is a surface. I tried to make it a little bit easier by saying, let's graph something that gives us a surface. Now, if you graph this function of 2 variables, that's one of the ones whose graph is a saddle surface. And if I restrict you to looking only at the portion of that saddle that lies atop a disk, then you'll get a sort of a Pringle shape. Okay, so that's the surface over which I'm going to do the integral. Well, the integrals, because Stokes' theorem is a statement that 2 integrals are equal. And since you guys have the opportunity to review this on a YouTube video, I'm going to kind of fly through all the calculations that I've written out for you. I'm going to compute both of these integrals. So I've already told you what the surface is and what the vector field is. Those are one of the ingredients on each of the two sides. I have to figure out the corresponding set on this side, the curve on this side, and I have to figure out the new vector field on that side. So I need a curl of the vector field to be the other integrand on the right-hand side. And here it is, I did it for you. And you need to know the curve on the left-hand side, but that's the boundary of the Pringle. That's what you would get is it's the part of the graph that lies just above the unit circle, not the unit disk. I don't even know if I want to try to draw this for you, but it goes up and then down and then up and then down. All right, so now I have all the four ingredients, on the left-hand side a vector field and a curve, and on the right-hand side a different vector field and a surface. So here I go. You want to compute a line integral? You got to parameterize your curve. The curve in question was part of the graph of a function of two variables, but only the portion of the graph that lay over the unit circle. So I parameterized the x and y coordinates in the predicted way, and then the z coordinate just has to match because we're looking at the graph of this function. So that's 7 times the x coordinate times the y coordinate. And when you, so that's the function I will use to parameterize the curve. My parameter has to come from this interval. You have to rewrite the vector field in terms of this parameter t. So of course I just went through and I substituted in every x and y and z. I replaced by this x and that y and that z, and you get a bunch of trig stuff. You also have to replace the integrand that shows up. That's your differential on the curve. And when we're computing these line integrals with a dot product, we just multiply the dt, this differential of the length in the parameter space, gets multiplied by this, essentially the fudge factor. This is your velocity vector. So I just differentiated the top line to get the velocity vector. So this is how you compute a line integral, right? You replace the curve with your parameter space. You replace the vector field with, you just substitute away all the x's and y's and z's, as I did. And you have to take the dot product with your tangent vector, which is the velocity vector. So it's a dot product. You just take the dot product of this top row here with this row. So this product is here between the parentheses. This product is there. And this last product, when you expand it out, it actually has 4 terms. And, well, it's just a bunch of long trig integrals, but let me point out that most of them have an odd power on either the sine or the cosine, and that makes it easy for you guys to compute those integrals. I know you had a chapter on that in Calc 2. As it turns out, when you integrate all the way from 0 to 2 pi, they just all turn into a 0. The only ones that survive are the ones that have an even exponent on both the sine and the cosine. And for those integrals, when you integrate all the way from 0 to 2 pi, it takes a little while, but you know how to make the computations. The integral of sine squared over this integral is just a pi. Sine to the 4th gives you 3/4 of a pi, and that other one here gives you 1/4 of a pi. So with the coefficients thrown in, I get some number. Nothing special about the number, it's just what the left-hand side comes out to. On the right-hand side of Stokes' theorem, you compute a surface integral, and you guys know the game you have to play there. You have to parameterize your surface. Since I said my surface was going to be the graph of a function, I just used the simple, I've called it the cheater's parameterization. X is a synonym for u, or u is a synonym for x, y is a synonym for v, and there's the function I'm graphing. My parameters themselves have to come from the unit disk. Your new vector field has to be rewritten. You got to get the x's and y's and z's out of there, so I did it. I just substitute them away. The tu cross tv part that goes into the differential, that's also in these special cases when you're just graphing a function. You may recall that there's a partial with respect to x here, a partial with respect to y there, and just the number 1 shows up. Those are just the columns of the derivative of my parameterization function from R2 to R3. And so here you go, computing that right-hand side integral. Instead of integrating over the surface, you're just integrating over your parameter space. You substitute away all the x's and y's and z's to turn them into u's and v's, and you need to compute a dot product with your normal vector. That replaces the differential. So it's a dot product. I computed the product of the first terms, the second terms, and the third terms. There you have it. And that's what I have to integrate over the unit disk, so I decided to do that in polar coordinates. I should have written r on the outside and theta on the inside because, as in the previous integration problem, most of these integrals are actually going to give you a 0. There's only a couple that remain. By the way, when you switch to polar coordinates, don't forget to write it as r d theta. So keeping only there's only 2 integrals that will remain because of the odd exponents. And so this is what you are left computing the integral of with respect to r. I already put in this extra r, I already factored that in. So that's why it says 3r instead of 3, for example. And a couple of Calc 1 integrals to do. Very easily, it just comes out to the same exact answer that I had on the previous integration problem. So I have now verified Stokes' theorem. Okay, got a lot of silence out of you, and I got 1 minute left. So let me just tell you, this is what we'll do on Friday. This is Gauss's divergence theorem, and it's one more theorem that says one integral is equal to another integral. I was kind of running out of letters now, but in this case, my integral on the right-hand side is a 3D integral. So I need a chunk of 3-dimensional space that I'm calling M. Its boundary will be a surface in 3-dimensional space. And on the left-hand side, I've got a vector field again, because I'm doing a surface integral. What shows up in the corresponding part of the right-hand side is its derivative. It's a kind of a derivative, which is in this case the divergence of that vector field. And then here you'll have a scalar valued function, which you're integrating over a chunk of 3-dimensional space. The kind of integral we're talking about on the right-hand side is just one of those 3D integrals like we had for Fubini's theorem. Figure out what your chunk of space is, and you integrate as x goes from something to something, y goes from something to something, z goes from something to something. This will be a scalar valued function of x, y, and z. This will be dx, dy, dz, and off you go. You might use the change of variable theorem if you like, doesn't matter. And the left-hand side is a surface integral. So I will pick up with this next time. I'll show you the special cases and stuff. I will just point out, because you asked, somebody asked, if your surface happens to be, no, I didn't write it out. If your surface happens to be something with no boundary, then the surface integral that you have to do will be, on the other side, no, you know what? I'm making it more complicated than I've run over. I'll show you that special case, that application on Friday, but it will be an application of Gauss's divergence theorem. All right. Any final comments or questions? We got this far.
Dr. Russell?
Yes, go ahead.
When you were doing your example, in the first case, why did you first use a cosine and sines? In the second case, you first used u's and v's. But for the u's and v's case, you ultimately switched to r's and thetas, right?
Yes, but the reason that I use sines and cosines here is you shouldn't really be asking about sines and cosines. You should be asking, why did I use a t here and a u and v there? And that's because the left-hand side is a line integral. You have a curve to parameterize. You parameterize curves with one parameter. So how do you get to each point on that curve with just a single number t? If you're asking, why didn't I try the cheater's parameterization? Because on a curve, I would have had to say something like, I don't know, like this. Is that how I would get my x and y coordinates? And then I would have to use this for my z coordinate. And I could do that if you want, but of course I'm only parameterizing the top half of the circle here. So it isn't really a question of why did I use sines and cosines, but you should be asking, why didn't I just use t? And I could have, but it actually gets more complicated for a circle. And of course here, this one on the right-hand side you're doing is surface integral. You need to parameterize the surface, and the parameterizations of a surface need two parameters. So I could have jumped straight to something like u times the cosine of v, comma, u times the sine of v, comma, 7 times u squared times cosine of v times sine of v. Yeah, sure, I could start using sines and cosines right away, but the fundamental fact is I gotta have two parameters to parameterize a surface and only one to parameterize a curve. Check it out. You guys have to understand that. I know that there's a lot to understand here, but on a basic level, about Stokes' theorem, you got to realize that one side is talking about line integrals, and this would be the way that you would compute a line integral in a very general setting. And the other side is a surface integral, and this would be the general approach that you use to compute a surface integral. You always begin with a parameterization, but it's one parameter here and two parameters there. All right, guys, I'm going to call it for today. We will discuss Gauss's theorem next time. I've already got the slides ready. But make sure that you understand at least the material that we have done today. I know I went really fast on the calculations, but I know that that's because you can look them up. You guys can go get all the details and watch it as slow as you want. I'll have that up later today, okay? And I will have office hours too, so come back later today if you want to ask me about this stuff. All right, guys, thanks for coming, and I will see you on Friday.